Well, let's dive straight into the wonderful world of light and optics. First, let's take a look at speed, frequency, and wavelength. Speed of light is 3 times 10 to the 8 meters per second in air and in a vacuum. It gets to be different speeds once you try to put them through different mediums that it can travel through. But the main thing is that we're mainly going to use 3 times 10 to the 8. F is frequency, measured in hertz, and lambda is wavelength, measured in meters. So, higher the frequency is, the lower the wavelength is going to be. You're going to see that as a reoccurring theme throughout this whole topic. Let's take a quick look at the electromagnetic spectrum. The electromagnetic spectrum, sometimes you might see it as EMS, is the full range of waves that can be given off by excited electrons. Now this includes waves from visible light, it includes radio waves, all the way up to gamma ray. So something from very harmless to things that get really hot and radioactive. The electromagnetic spectrum arranges waves based on their wavelength and frequency. From left to right, you can see that frequency is increasing. So if you look at frequency right here, we're going from 10 to the 4 hertz, from 10,000 hertz, all the way up to 10 to the 20. And visible light is a very small portion, about this range right here. So all electromagnetic waves travel at the same speed. So that speed that we mentioned earlier, remember this? C equals F lambda, speed of light, 3 times 10 to the 8 meters per second. That is the same speed for everything on the electromagnetic spectrum. Same theory or concept, that as frequency increases, wavelength decreases. So the low energy radio waves that are used to pick up signal on your radio, it has a relatively low frequency and an incredibly long wavelength. And this is the same for all electromagnetic waves. So if I ask you to calculate frequency given the wavelength, you use this equation and you use 3 times 10 to the 8 for the velocity. Side note, a light year is the distance an electromagnetic wave will travel in 1 year, which is about 5.87 trillion miles. Very fast. Types of electromagnetic waves on the spectrum. So radio waves have the lowest frequency, longest wavelength. It's used for communication, and AM wavelengths are longer than FM, which is why they're able to transmit AM radio stations a longer distance than FM. Microwaves have higher energy than radio waves. It's used to heat food, it's used for radars, it's used in cell phones. It's not natural. It doesn't occur very much in nature. We kind of produce this ourselves. Water and fat absorb energy from microwaves, making them hot. And microwaves can only penetrate up to 2 centimeters. So that's why your food is cold in the middle when you heat it up in the microwave, because it's only reaching 2 centimeters all the way around. So what I do is I put a hole in the middle of my food, so there is no middle. So everything's hot. There you go, learn something new every day. Infrared waves. They can't be seen but can be felt as heat. None of these you can see so far. Everything gives off infrared radiation. It's used in TV remotes, fire alarms, and heat lamps, and heat sensing cameras. Some animals see infrared waves. Visible light. This is the one we can see. Roy GBIV. That is the spectrum of visible light: red, orange, yellow, green, blue, and then ends up with violet. Color depends on frequency. Now we covered infrared, which is before red, and then ultraviolet is after violet. Ultraviolet, present in sunlight, used in tanning beds, sterilization, and food processing. Some insects can see them. So this is the one that you use sunblock for, and you get the special sunglasses that blocks the ultraviolet rays. It occurs naturally, but it can be dangerous to your skin and to your eyes. So we're continuing types of waves. We have X-rays, which have enough energy to pass through most materials, but not lead. Lead is one of those materials that it can't pass through. It's commonly used to see through objects like X-ray machines, to see bones, to see dental work, stuff like that. It can occur naturally in stars. Gamma rays. This has the highest energy of all the waves on the electromagnetic spectrum. It's emitted by radioactive materials, can be found in the hottest regions of the universe, only when stars are like exploding and stuff like that. And you know, star is like a sun basically. And so exploding stars and radioactive materials, that's the kind of stuff that gives off gamma rays. Alright, remember, all electromagnetic waves have the same speed, 3 times 10 to the 8 meters per second, unless a particular problem says otherwise. That's the speed. These are all waves. The only thing that differentiates them are wavelength and frequency. The bigger the wavelength is, the lower the frequency is. And the lower the frequency is, the bigger the wavelength is. Or the bigger the frequency is, the lower the wavelength is. So frequency and wavelength have like an opposite relationship. The higher the frequency is, the higher the energy is. So if I'm asking you which one has more energy than the other, you can just look at the frequency. All right. So frequency and energy would be what you would call directly proportional, meaning when one goes up, the other one goes up. Now, wavelength and frequency / energy are inversely proportional, meaning when one goes up, the other one goes down. And that's all I have to say about the electromagnetic spectrum.